Welcome to the exciting world of gas power cycles. This is where we explore how engines, like the ones in cars, planes, and power plants, convert heat into useful work. Gas power cycles are the heart of modern transportation and electricity generation. They are fast, powerful, and everywhere around us. But underneath the hood, these systems are just a clever application of thermodynamic principles designed to maximize efficiency and minimize waste. Throughout this chapter, we'll break down how these cycles work, starting from the simplest ideal cycles like the Otto and Brayton to real-world applications. You'll see how pressure, temperature, and volume interact to produce power and how engineers tweak these parameters to get the best performance. Think of this chapter as a roadmap to understanding the engines that literally move our world. Let's dive in. Let's introduce the concept of gas power cycles in a simple and clear way. These cycles are all about generating power, whether it's to keep your car moving or to produce electricity at a power plant. The key idea here is the working fluid. In gas power cycles, the working fluid stays in the gas phase from start to finish. There's no phase change into liquid like you'd see in steam cycles. It's just gas all the way through, compressed, heated, expanded, and then cooled. Also, it's useful to split gas power cycles into two main types: internal combustion engines, where the fuel burns inside the engine, like in cars and motorcycles, and external combustion engines, where fuel burns outside, like in gas turbines and jet engines. Keep this structure in mind: gas, no phase change, and two main engine types. It makes the rest of the topic much easier to grasp. Let's go over some basic but essential terms you'll use again and again when analyzing power cycles. First, we have the concept of an ideal cycle. Think of it like a perfect world version of the cycle, where all the messy things like friction and losses don't exist. It's a simplified model that helps us understand the theoretical limits of a system. Next is thermal efficiency. This is one of the most important performance indicators. It simply tells us how much of the heat energy you put into a system gets turned into useful work. Higher efficiency means less wasted energy and better performance. And finally, Carnot efficiency. This is the gold standard, representing the maximum efficiency any cycle can achieve if it operates between two temperatures. No real engine can beat it, but it gives us a useful benchmark. Understanding these three ideas, ideal cycle, thermal efficiency, and Carnot efficiency, will make the rest of power cycle analysis much clearer and more structured. 3. The Carnot cycle. Let's talk about the Carnot cycle, often called the perfect cycle in thermodynamics. It's made up of 4 ideal processes that are completely reversible: 2 isothermal, constant temperature, and 2 isentropic, no heat transfer, just expansion or compression. First, heat is added isothermally, then the gas expands isentropically to do work. After that, heat is rejected isothermally, and finally, the gas is compressed isentropically to its starting point. The Carnot cycle gives us a simple and powerful efficiency formula. It only depends on temperatures, not the working fluid or pressure. The higher the temperature difference, the better the efficiency. But here's the catch. In real life, Carnot cycles are not practical. Isothermal processes are very slow because heat transfer at constant temperature requires massive heat exchangers. That's why real engines use faster but slightly less efficient cycles like Otto or Brayton. Think of Carnot like an unreachable goalpost. It shows us what's theoretically possible, but not what's practical. 4. Air standard assumptions. Let's make gas power cycle analysis easier by introducing some simplifying assumptions. Instead of dealing with the complex reality of combustion and exhaust, we model the system using clean, idealized conditions called air standard assumptions. Here's the idea. First, we assume the working fluid is air and it behaves like a perfect ideal gas. This skips all the chemical reactions and focuses on pure thermodynamics. Second, all processes are considered perfectly reversible. No friction, no losses, making calculations simpler. We also replace combustion with a simple heat addition process and exhaust with heat rejection. This means we don't need to model fuel burning or exhaust gases, just focus on heat transfers. Finally, there's an even simpler version called the cold air standard assumption. It treats air's specific heat as constant at room temperature, which avoids messy temperature-dependent calculations. With these assumptions, the math becomes cleaner and we can focus on the core performance, making it easier to understand and compare different engine cycles. 5. Otto Cycle, Ideal Spark Ignition Engine Cycle. Let's look at the Otto cycle, which is the ideal cycle behind gasoline or petrol engines, like the ones in most cars. This cycle is made up of 4 simple steps that are easy to remember. First, the gas is compressed without losing any heat. That's called isentropic compression. Then, we add heat quickly at constant volume, just like when the spark plug ignites the air-fuel mixture. Next, the gas expands isentropically, pushing the piston down and producing work. Finally, heat is rejected at constant volume, just like the exhaust stroke in an engine. The key takeaway here is efficiency. The Otto cycle's efficiency depends on the compression ratio, how much we squeeze the air-fuel mixture before ignition. Higher compression means better efficiency, but we can't increase it too much because of engine knock, when the fuel ignites too early and damages the engine. This simple relationship between compression ratio and efficiency explains why sports cars have higher compression ratios while regular cars balance it to avoid knocking. 6. Diesel cycle, which is the foundation for diesel engines, used in trucks, buses, and some cars. Just like the Otto cycle, it has 4 steps, but there's one key difference. Instead of heat being added at constant volume, diesel engines add heat at constant pressure. So after isentropic compression, fuel is injected and burns while the piston is still moving, keeping the pressure nearly constant. Then it expands isentropically, doing useful work, followed by constant volume heat rejection. The efficiency formula looks more complicated because it includes both the compression ratio and something called the cutoff ratio, which is the point where fuel injection stops. One important feature of diesel engines is that they run at much higher compression ratios than gasoline engines, which boosts efficiency. The good news is, diesel fuel is less prone to knocking, so these engines can safely operate at these high compression levels. In short, diesel engines trade off a slightly longer heat addition phase for the ability to compress more and burn fuel more efficiently. 7. Stirling and Ericsson cycles. Let's look at 2 special cycles that are known for their high efficiency, Stirling and Ericsson cycles. Both of these cycles have something in common. They include 2 isothermal processes, meaning heat is added and removed at constant temperature. The Stirling cycle uses constant volume processes for the other 2 steps, while the Ericsson cycle uses constant pressure processes instead. What really sets these cycles apart is regeneration. This means they recycle some of the heat within the cycle, which reduces how much heat they need from the outside. Thanks to this regeneration, both cycles can theoretically reach the same maximum efficiency as the Carnot cycle. In simple terms, these cycles are clever designs that reuse heat and aim for top efficiency. But in practice, they are more common in niche applications like Stirling engines for submarines or quiet generators. 8. Brayton cycle, which is the core of gas turbine cycle. These are the engines you find in jet planes and power plants. The Brayton cycle is all about high-speed continuous power, very different from the up and down motion of piston engines. It has 4 steps. First, air is compressed isentropically. This means without heat loss, like in a jet engine compressor. Then we add heat at constant pressure, like in the combustion chamber. The high-energy gas expands isentropically through a turbine, generating power. Finally, heat is rejected at constant pressure before the cycle repeats. The efficiency of this cycle depends on the pressure ratio, meaning how much the air is compressed before combustion. The higher the pressure ratio, the more efficient the engine becomes. The Brayton cycle is popular because it's simple, compact, and capable of producing huge amounts of power quickly, perfect for aviation and large-scale electricity generation. 9. Brayton cycle with regeneration. Let's take the basic Brayton cycle and make it more efficient using regeneration. The idea is simple. Don't waste the heat leaving the turbine. Instead, we use a heat exchanger, called a regenerator, to capture this heat and preheat the compressed air before it enters the combustion chamber. This reduces the amount of fuel needed for heating, improving overall efficiency. The effectiveness of this regeneration process tells us how much of the available heat is actually recovered. But regeneration doesn't always work. It only helps when the turbine exhaust is hotter than the air coming out of the compressor. If not, there's no useful heat to recover. In summary, regeneration is like recycling heat energy. It can make gas turbines more efficient, especially in industrial applications and combined cycle power plants. 10. Brayton cycle with intercooling, reheating, and regeneration. Let's discuss a more advanced version of the Brayton cycle, one that uses intercooling, reheating, and regeneration all together to boost performance. Intercooling happens in the compressor. By cooling the gas between compression stages, we reduce the work needed to compress it. Less effort means better efficiency. Reheating happens in the turbine. By adding heat between expansion stages, we keep the gas hotter for longer, which increases the work we get out of it. Regeneration is like recycling heat, capturing waste heat from the turbine exhaust to preheat the compressed air before combustion, saving fuel. The real magic happens when we combine all three: intercooling, reheating, and regeneration. This combo significantly improves cycle efficiency and power output, making it popular in high-efficiency power plants and advanced gas turbine systems. 11. Jet propulsion cycles. Let's talk about jet propulsion cycles. These are the cycles behind how aircraft generate thrust. The most basic is the turbojet engine, where air is compressed, mixed with fuel, burned, and then the hot gases are expelled at high velocity to produce thrust. The amount of thrust depends on how much the velocity increases. This is captured by the thrust equation, which is simply the difference between exit and inlet velocities. But it's not just about thrust, it's about how efficiently we convert fuel energy into useful propulsion. That's where propulsive efficiency comes in, measuring how much of the input energy actually pushes the vehicle forward. Modern aircraft use turbofan engines, which add a big fan to move more air and improve efficiency, especially at subsonic speeds. For high-speed applications, we have ramjets, which skip compressors altogether and rely on high-speed airflow to compress the air naturally. These are most efficient at supersonic speeds, making them ideal for missiles and fast jets. In short, different jet engines are optimized for different speeds, but they all follow the same principle: accelerate air backward to push the aircraft forward. 12. Second law analysis of gas power cycles. Let's look at gas power cycles from a second law perspective. This means we go beyond just energy amounts and focus on energy quality. The key concept here is exergy, which measures how much useful work we can actually get from energy. Exergy destruction tells us where energy is wasted due to irreversibilities like friction and heat losses. To evaluate performance, we use second law efficiency. It shows us how much of the available useful energy we really recover. A higher value means less waste and better design. Entropy generation is the culprit that lowers efficiency. By identifying where entropy is created, we can find weak spots in the cycle and know exactly where to improve. This second law approach helps engineers go from how much energy to how well we use it, leading to smarter, more efficient power cycles.
Let's end by talking about how to improve fuel efficiency in everyday driving. These are simple, practical tips anyone can apply. First, driving at moderate speeds, around 55 miles per hour, is the sweet spot where most vehicles achieve the best fuel economy. Try to maintain a steady pace and avoid frequent braking, which wastes energy. Extra weight and roof racks increase drag and fuel use, so travel light. Keep your tires inflated because low pressure increases rolling resistance. Air conditioning is useful, but also consumes extra fuel, so use it wisely. Choosing vehicles with high miles per gallon, MPG, saves money in the long run, especially if you drive frequently. Cruise control helps keep a constant speed on highways, reducing fuel consumption. Avoid idling for long periods. It burns fuel without moving you anywhere. Finally, regular maintenance like oil changes and air filter replacements not only extends engine life, but also keeps your vehicle running efficiently. Small habits lead to big savings.